So now we'll talk about the uncertainty principle. What is the uncertainty principle? Basically, it's how uncertain are we at measuring certain things of particles. In Newtonian physics, there were no limits on how small the uncertainties can be. A particle at any instant of time has an exact position and an exact momentum, and we can measure both precisely. Heisenberg came along to describe what was going on, and he said, no, we can't measure both simultaneously with good precision. And this kind of came from the wave-particle duality. What Heisenberg was saying was that the more precisely the position is determined, the less precisely the momentum is known, and vice versa. Basically, you can only the more precise you can get in one thing, the less precise you can get in the other. This here is the uncertainty equation, where x is your position and p is your momentum in the x direction. The other side of the equation, I've seen several forms of it, but we're going to concentrate on the left side here of it. And so the product of the two have to be greater than or equal to Planck's constant, or some form of Planck's constant. So again, this was a result of the wave-particle duality that we talked about previously. Just to kind of review that, it came from the double slit experiment, where when you send particles through a barrier that has a double slit, the result is an image of that double slit on the screen. Whereas waves, when you send those through a double slit, you'll have a wave interference pattern, and that led to the wave-particle duality when used through electrons. When we did it one at a time, it still showed the wave interference pattern, where the electrons were acting as a wave. But once the electrons were observed to see which slit they were going through, they acted as a particle again, showing the image of the double slit on the screen. And, there was something weird going on, and they said, just by observing it, it had changed into a particle. Now, just to be clear, we'll talk about the observer effect versus the uncertainty principle. These two are not the same. Basically, the observer effect, that has to do with something being directly observed. It could be due to the equipment, it could interfere with what's actually going on. With the uncertainty principle, it doesn't have to be observed for something to be understood mathematically. So on the subatomic level, the particles can't have precise position and precise velocity at the same time, whether it's being observed or not. It's just the way things work. It's not from the equipment, it's not observer interference, it's just the structure of the matter itself. So there are two different concepts, but we'll talk about the uncertainty principle here. So again, this was due to the wave-particle duality from the double slit experiment. So what the double slit experiment showed, that electrons could not be observed as both a particle and a wave. Particle, we can measure the exact position. With a wave, we can measure the momentum. So we couldn't observe them happening both at the same time. We could measure one or the other, but not both. So when it acted as a particle, we could measure the position, we could know where it is, but we did have some uncertainty. And as a wave, we could measure the velocity, and equivalently its momentum. We could tell how fast it was going, but again, we had some uncertainty as well. So when it comes to light, if you send light through a slit or some kind of hole, what happens to it? Now, intuitively, you have a slit here, and on the screen it's going to be projected in that same size as the slit. As that slit gets narrower, what you would think is that the light would also get narrower, which is true to a certain point here. But when it gets to a certain size, what happens is the light actually starts spreading out, and this is where the uncertainty comes in. It's something that happens. I wish I could show you to demonstrate how it happens. There's tons of videos on YouTube, but again, this is demonstrating what Heisenberg's uncertainty principle is. So here, going back to the equation, you have you have position and you have momentum in the x direction. It has to be greater than or equal to a certain constant. So here you can see if you have a certain opening, you're going to get that that size light. You get narrower, it gets narrower until you get to a certain point, and then that gets it actually gets wider. So what's going on here is that you're seeing a more precise position, and as the light is going through here, as it gets narrower, your position becomes more accurate. Now, once you get to this point, your position becomes so accurate that your momentum becomes less accurate or less precise, because the product here has to be greater than this number here. So as this one gets smaller and smaller, this one has to get bigger. So the uncertainty, the product in the uncertainty must remain greater. So in order for the equation to hold true, the more precise you get in position, the less precise you get in momentum in the x direction. And hence, as the slit gets narrower, that's where your precise position comes in, and the momentum becomes greater, and you get a wider band as opposed to a narrower. So it's quite counterintuitive, but that's where the uncertainty comes in. So basically, we can't know where something is and how fast it's going. When tested, even atoms at the temperature of absolute zero, they still jiggled a little bit. So again, we can know where something is or how fast it's going, but we can't know both precisely. So a way to kind of grasp this or think about it is on a larger scale. So imagine if you took a snapshot of a wave at an instant in time and you showed it to someone. So you'll know where that wave is, but you don't know where it's going. Another way to look at it is if you're trying to map out balls on a billiards table, but you're doing this blindfolded and you're doing it with a pool stick. So you're using the pool stick as your feelers, and as soon as you find where a ball is, it starts going, and you no longer know exactly what it's doing. So it's that kind of thing where it's kind of impossible to map exactly where all the balls are on the table. Same thing with the subatomic particles. You can't map it out. You don't know exactly where it is and how fast it's going. So kind of now that we know a little bit about the uncertainty principle, we can enjoy humor in today's shows. And here's a little comic that I like, and it's actually one of my favorite shows. So I know you know about the certainty principle, so I hope you find humor in this.